Alright, in this video I'm going to show you how we could analyze a structure under time varying load or under varying load. Okay, so let's see. Let's go to we're going to use APDL. Alright, so I'm going to consider a very simple truss, very simple beam frame structure. So structural, the analysis is going to be structural. We're going to use beam elements, so go here, pick the 2-node beam element, and I'm going to make sure that I'm going to use cubic shape functions. Alright, and material property, let's consider steel, which has modulus of elasticity of 200,000 megapascal or 200 gigapascal. Alright, so then for section of the beam, I'm gonna consider a circular section. The radius, let's say, is 5 millimeter. Alright, and then the model. So I'm gonna the simplest structure we can think of, we're gonna do. So let me start with origin. My first key point is my origin. Then the second key point, let's say, is 500 millimeter to the right and 500 millimeter, in X, 500 in Y direction. And then my third point is 1000 millimeter to the right. So as I said, I'm gonna model a triangle. So alright, so these are, I wanna, like this is vertical, I wanna make it horizontal. So let me delete this last key point and then do that again. So delete number 3 and create number 3 again. Yeah, the mistake I made was okay, so let me fix it. Okay, so we have now a horizontal frame. Okay, so next I'm gonna connect these guys, these lines, these points by a straight line. Okay, and then next I'm gonna mesh them. For meshing, I'm just gonna consider one element per line. So to do that, can come here, mesh size, all lines, do just one per one per line, one per member, and then now mesh all the lines. Alright, so then loading, analysis type, we're gonna do transient analysis. So then define the loads. So let's define the loads. At first I'm gonna put the boundary conditions, you know, displacement boundary conditions, this key point and this key point. I'm gonna fix them both. You know, okay, let me have it simply supported. So on this key point, let's fix everything. The other one, I'm gonna leave X be free. So let's choose everything but UX. Oh, technically rotation about Z must be free, so everything but UX and rotation I'm gonna have it free too. At that point. Alright, so about this place, let me change that too. So let's go here. I want to have the rotation about Z axis to be free at that point too, but I want to fix UX there, so only rotation about Z is free at this point. Okay, then I'm gonna apply a time varying load. So let's see how we could do that. If you go here, define loads, apply, you can here define a function. As you see here, you can define a function here in terms of time. So for example, just as an example, let's say my force is 500 times sine of, I'm sorry, 500 times sine of time. So our variable is time. Alright, so let me erase this extra parentheses. Alright, so this is our function, let's say, and we can graph the function and take a look at that. So I want to have my x range be 0, graph it, you know, with from 0 to 10 seconds, and then have it the number of points to graph 100. So let's see the function if you like. Yeah, here is my function, sinusoidal function. Alright, so we can save this. We can save this function as, you know, let's go save it on OneDrive. Yeah, so what do I call it? I call it force. Alright, so save it. And now I close it. Alright, so now we go here and let's plot the key points. So I'm going to apply this force to point 2. Okay, so we go, say we want to apply the force to key point 2, and then okay that. It has to go, I'm going to put it in Y direction. For the value, we're going to use the existing table, and then so, oh, okay, I forgot to read, you know, we defined the function, but we have to read it too. So let me go here, You see read file, you have to go here and then say I'm gonna read the force function, and then it says table parameter name. We are gonna call it, you have to put a name. So let's say we put force F1, then I OK it. Now let's go to where we were and then apply the force. Okay, so go here, key point 2, and it's gonna be in Y direction, existing table. Now you see we have F1 available there to pick. So we pick that, and that force is going up. Alright, so that was a positive force. Alright, so then we have all forces done. We come here, analysis type. We have some solution parameters, solving parameters we need to set up. My analysis is transient, but solution controls, let's see what we gotta do. So here you can say, time at the end of load step. Let's say I want to model this for 10 seconds, and you can here see specify number of sub steps to solve it. You can say 100, for example, as your number of time steps, number of sub steps. Then it's gonna march from 0 to 10 seconds with 100 steps, and then solve the structure. Alright, so and then here you can say that as you're solving this, write all the sub steps solutions in the output file. Then you can then plot it later. Or if you don't want to do that, you can just, just write the last step, write the last sub step only. That's the default. And yeah, so I'm gonna pick this one, write every sub steps. So there are different options. For example, you can say write every 10 steps. You can ask to the software to do that for you. But I want to see everything. Okay, so every sub steps is here. All right. Okay, so we did this. Now let's solve it. I want to show you guys this log file, the output window, see how it works. So now it's solving it. Oh, the solution was so fast. Okay, so we did the solve it. Now let's look at the solution. We are gonna see the solution here. We can look at it here. Time history. See time history post-processing. You can use this dialog window to look at your output. So we have the time as our x-axis. So you come here, you can add a data, and then degree of freedom solution. I want to see y displacement of one of my nodes, which is important one, was node number 2. Node number 2, or key point number 2, was here. So you can type it here 2, then it's gonna pick node number 2, right? And here's our solution. Now we can our displacement that I was looking for is listed here. Now I can plot it. Can come here, click on this graph, and now we should see the solution. So this is how displacement looks like. See, it's like point, you see how it varies. It's like 3 times 10 to negative 2 millimeter. So and it's varying sinusoidally, harmonically. You know, um, the unit is gonna be millimeter because I was did my forces in Newton. All my dimensions were in millimeter, and my mass velocity was megapascal. So the output is going to be in millimeter. All right. So since this was a linear elastic analysis, technically the transient analysis we did here, you know, is not gonna have a lot of value because, as you see, input was sinusoidal, output sinusoidal, and exact function. And you know, since there is no nonlinearity, you know, as the force changes, we could actually find a new response by just scaling the output. So we could technically do that. But if your behavior of material is like nonlinear, then this will have more value to do. Okay, so alright, so this is how it works. We apply and add new data that you want to plot like this. Alright, so I hope you find this video useful.